G'day everyone, how are you going? We're back in term 3 now, which this is the business end of the year, it really is. If you're working through the course at the moment, my strong suggestion is hit the ground running. It's a sprint for this term. You don't have a moment to lose. Every weekend make significant progress on each of your subjects. If you wait till week 4 or week 5 to get started, you will run out of time. Please start now. Work hard every day from now till your exams. Social life, sporting life, put it to one side. Get the academics happening. It will pay dividends in about 12 weeks' time. I promise you that. So what are we doing in Spec today? Well, today's about implicit differentiation. Most functions, or many functions, we can write explicitly. What does that mean? This is an explicit function, meaning that I can write y in terms of x, or one variable solely in terms of one other variable. Okay? All the y's are here, just one of them. All the x's are over here. That's an explicit function. And therefore I can differentiate that one pretty easily. That's just our regular differentiation ideas. What do we got here? Power out front, lower the power by 1. Thanks for coming. Power out front, lower the power by 2. Thanks for coming. I'm done. That's pretty simple. But what if I had something like this that maybe I can rearrange, maybe I can get it into a y equals, but in this one I'm probably not going to, because I've got a y to the power of 1 and a y squared. I'm probably not going to be able to bring them together. I might find something, but it's probably not going to work. So how do we do an implicit function? Okay, I've got up over here. I've taken exactly what I had here, and really I've just worded it slightly differently. I've now said I want to take the derivative of both sides. Now before I get there, I want to just talk about this one for a minute and say, how do we actually do this? What do we do here? Well, I'm going to do the same thing. It's y equals 3x squared plus 2x. I really do the same as what I've got here. I'm going to take dx of that side, the derivative with respect to x. And I'm also going to take dx of that side. So I'm really just doing the same to both sides. Adding 5, taking 5, multiplying by 5, derivative both sides. That's all I'm doing. On the left here, this just becomes dy dx. It's kind of like a fraction, but it's not really. Okay? So we generally don't write the line, but if you do, it's no big issue. Dy dx, that's the rate of change of y with respect to x. And then I would do the same over here, but the different thing here to implicit differentiation is that when I want to do that, or do this, then the thing that I'm taking the derivative with respect to is exactly the thing that I have over there. So then all my regular differentiation rules apply. Power out front, lower the power by 1, that means I've done my derivative. Okay? Now you might find that your teacher, when you learnt this in year 11, a bit of differentiation or whatever, and now in year 12, they might not have used this notation. Because when you're doing simple explicit differentiation, it can actually make it more difficult for students to understand what's going on. And you probably started with differentiation by first principles. Have a watch of that video. Let's have a look at 2 points. Let's move them closer together. What's happening? That's where we generally start. But this here is really what you're doing. You're just doing the same function to both sides, or the same operation. And then this is what we actually want. We write it like that, or we write y dash, or we write f dash x. They're all the same notation. But when you're learning, it's often simpler to start with just y dash. Keep it simple. Dy dx and f dash x tends to confuse. So this is what we're really doing, even with a simple explicit function. Right? But it's handy to know that, because that's the best way to now show what we're doing with implicit differentiation. Right? So I guess it's just finding the right tool for the right occasion. With this, it was simpler just to say power out front, lower the power by 1, blah, 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 product rule, chain rule, quotient rule, all of those. With this, it's better to show it this way. So, what am I going to do? Well, I'm going to just look at the first part first here. d dx of xy. Now, the rest of it will do as well, but I'm just going to do them in parts and then I'll build it together. So if I've got d dx of xy, xy is a product, x times y. So I've got to use product rule in there, okay? The product rule would say derivative of the first times the second. So derivative of the first, that's d dx of x times the second. And then the next part is plus the first times the derivative of the second. So that's just the product rule. Nothing too fancy there yet. All right? This I can do, because remember what I had up there just before. That really is the variable that I'm differentiating with respect to, and the variable I'm trying to differentiate. They're the same. So I can do that. This here is just going to be 1, because the derivative of x is just 1. Times y. So the first part's not so bad. Didn't need any implicit differentiation. This second part is where kind of the trouble comes in. I'm trying to take the derivative with respect to x, but of a different variable. Well, I can't do that, right? I can't use a ruler to measure the time it takes for you to run 100 metres. I'm using the wrong measure, right? And I can't use a stopwatch to measure the distance of a desk. It's the wrong measure. I'm on the wrong measure here. So I've got to adjust my measuring tape. What I do is this. Take just this part here for a moment. Let's come up here. I'm going to write d, but I'm going to put the dx over here. Okay? And then put y over here. So I've really just spaced it out a little bit. That's all I've done. Now I'm going to turn this one into d dy and turn this one into dy dx. Now, think of them like fractions. I've added something to the top, something to the bottom. They cancel out. Not exactly, they're not fractions, but we can think about it this way. This kind of cancels out, if I wanted it to, and that there is exactly what I started with. You might go, well, you're just making it harder. Well, no, I'm not, because now I can ignore this part here for the moment. Think about putting him at the end there. And now I want to take the derivative with respect to y of y. Well, that I can do because I've got the right measure now, don't I? I've got with respect to y of variable y. So I've got the right measure. So the derivative with respect to y of y is just 1. But I can't forget this guy that I moved on in here. Right? So I just say 1 times dy dx. So the answer to this part here is going to be the x. I don't do anything with him. The derivative with respect to x of y is actually 1 times dy dx. So this is times dy dx. So xy, derivative with respect to x, becomes this here. Okay? Now, we've got a few other things to work in here as well. So I'm just going to take this, I'll just scribble them over here. 1 times y plus x dy dx. Right, let's remember he's over here. I'm going to get rid of that. You rewind if you need to see it again. Let's do the second part here. Let's do the second part. Right, so now we've got the derivative with respect to x of y squared. So we've got d dx of y squared. Again, my measure is wrong. I've got volume here and I've got time here. It's not going to work. Let's split it up. d dx, dy, remember these kind of cancel, of y squared. Now I've got the right measure, don't I? So differentiate this with respect to y. That means all my normal rules apply. Power out front, lower the power by 1. This, when I apply d dy to that, I get 2y. Power out front, lower the power by 1. Multiplied by dy dx. So the derivative of y squared with respect to x is 2y dy dx. Okay? Now, Again, rewind if you need to see that again. I'm going to get rid of that. Now this last part over here, we don't really need to, it doesn't matter what variable we're differentiating with respect to when it's just a number, because the answer is 0. Why? What is the gradient of a straight line? Because think, here's that line. Here's the x-axis, here's the y-axis, here's 4. What's the gradient of the line 4? Well, I don't really care what, it's 0, right? So I don't need to worry about that bit there. So then this, let's piece it all together, becomes this. It's going to be y, or one lot of y, plus x dy dx, plus 2y dy dx equals 0. Okay, I'll get rid of these. So, now I've got that, I can now do a bit of tidy up, because just see this as the thing that I want to bring together. So, follow me if you can. I'm going to go dy dx, brackets, x plus 2y equals minus y. Just see that one, I move the y over to here. Common factor out front, x plus 2y. Therefore, dy dx is going to equal negative y over x plus 2y. So I now have dy dx. I have the gradient. Yes, it's in terms of x and y, but that's because it's an implicit function. Okay? I'm not going to just have x's or y's over here. Now, in this sort of question, you would normally be given this sort of thing and say, find the gradient when x equals 3 and y equals 2. You'd just go substitute them in. If you're only given one of them, find the gradient when x equals 2, well then just take the x equals 2, put it into your function originally, find the y value, and then come along, put both of them in here. So implicit differentiation, it's got a few tricks to it, most definitely. Got a few tricks. But once you see what's going on, rewind the video, see how I split up dy dx, or sorry, d dx, to become dy dx and d dy. That's the trick. That's the trick. Once you've seen that, and you can then put that into practice, it's not a difficult thing to do. Now, my word of warning here is, sometimes questions seem easy. Oh, look, I can just do this. And they actually not, right? Because you miss the implicit idea. Let me do one for you here. One of my students just before asked me this question, and I said, oh, gee, I think you've missed something there. And they couldn't see it until I explained. And then they went, ah, right. And hopefully he's got it now. Sine of xy. Differentiator. Well, okay, let's stop and think. If I had sine of 3x, then I'd have to see this not as sine of 3x, but sine of u, and u equals 3x. It's chain rule, isn't it? I can work dy du and du dx and then multiply them together. Or I can remember my rule and I can say, well, hang on, if that's the case, I need to take the derivative of that and throw it out the front, derivative there, and end up with that. So I've got to think, hang on, there's more than just sine going to cos. I've got to do a bit more. So back up to this one up here, I've got to see that it's the derivative of that that's got to come out front. Now the derivative of that, because it's x and y, has to be implicit. So I have to see that as that's going to be implicit differentiation. Now if you remember from before here, derivative of the first times the second with respect to x is just going to be y. Have a look back and see if you can see. First times derivative of the second with respect to x actually falls out as dy dx. Again, check back on the previous one. You'll tend to remember that one after a very short amount of time. That's the derivative out front, multiplied by, change the sign into cos of xy. So that, when we take the derivative of this, is going to be here. Now you might say, well, yeah, but is that y equals? Or, well, we've got to think. Because we've got two variables in here, this probably would be something like t equals, or q equals, or r equals, or whatever. It's some variable in terms of two others. Okay? So you might say, but what do we do there? Well, in these questions, normally nothing more. Normally it's differentiate and maybe substitute in, but that's probably it, you know. So they're a little bit different in the solving part of it once you get through a little bit more. This is kind of as far as they normally take them. You normally just ask to differentiate to show your skills. One you might want to try is this one, the square root of xy. That's a good little question because you've got a function and then two functions, so it's implicit, but it's product rule and chain rule in there. There's a little bit of playing around to get that one. Again, once you've seen it, it's not so bad. Quick recap. Over here, explicit functions, we've done them to death. We're pretty good here. Simple. But see what we're actually doing. d dx, d dx. Go back to the other part of the video. See it, rearrange. Here is where that rearrangement really comes into play because we need to rearrange the d dx to be d dy, dy dx. Okay, that's the little trick. Once you've got that sorted, all of this kind of just falls on out for you. Hope this one's helped. Welcome back to term 3. Enjoy your term. Hit the ground running. Do not stop from here. Watch the videos. Get on. See the others. Subscribe. Tell your friends. Watch the videos. Get on with the work. You'll enjoy it. See you later, guys.